Okay, welcome back. So today will be the concluding lecture for this course, Fundamentals of Semiconductor Devices. Hope you have been able to understand the basics of semiconductors and semiconductor devices in this course. I tried to make this treatment as unique as possible. Also tried to moderate the speed. For each of the topics that we have studied here, we have only covered most of the basics. There are far more things that can be learned in very great details and depth in each of the topic, whether it is transistor or LED or even just a PN junction. There are many things which we didn't cover because that will be an advanced course, or we have to move very fast, which will defeat the purpose of learning in this course, right. So today we shall have a recap of whatever we have done very quickly, and maybe try to see one or two unique type of questions that are also probable in entrance exams, so that you should be able to understand your concept or test your concepts better, okay, and then we will conclude. Okay, so we will come to whiteboard. So whatever we have studied in this course is that we had started with semiconductor bands that you now know, right. We have studied the EK diagram, the energy band diagram, right, energy band diagrams, which are very basics. We studied about doping and carrier concentration like electrons and holes, right. We studied about the Fermi-Dirac statistics to calculate electron hole concentrations and things like density of states, right, of carriers, right. We talked about recombination of carriers, how traps might lead to recombination of carriers, and decay of excess carriers. When you inject excess carriers, they decay, right. And along with that, we had studied the continuity equation, which we studied, which gives you sort of the transport equation for carriers in conjunction with things like drift and diffusion. We studied this carrier transport equations of drift and diffusion when it happens, which of course depends on things like mobility, carrier velocity, diffusion coefficient, and so on, right. We had discussed that, and from there of course we have the Einstein relation also. We move to basics of PN junctions, forward bias of PN junction, reverse bias PN junction, breakdown, and so on, capacitance, voltage, how PN junctions work. We also had studied Schottky junctions, that is metal semiconductor contacts, how they can form Schottky and ohmic barriers, the IV relation. They also have capacitance and so on. PN junctions can be also used as LEDs that we had studied in some details, can be also used as solar cells, which also we had touch base, and also can be used as photodetectors. There could be also photodetectors. Photodetectors can also be from Schottky junctions we had studied. Of course, photodetectors can be also in lateral MSM devices, and solar cell can be from different other kinds of architectures and materials also. LEDs also depend, the performance depend on heterojunctions. So there we introduce the concept of compound semiconductors and heterostructures. Compound semiconductors, CS, where I said group 3 compounds like arsenide phosphide and group 3 nitrides, semiconductor polarization and things like that, and transistor. These are some of the things that we had studied. We also had studied about transistors in some details. If you recall, we had studied about BJTs, and of course in heterojunction you have HBT, the advantages that they give, how BJTs work, what is gain. We had studied about MOS capacitance, MOS CV, and MOSFET. In that MOSFET we had also studied about things like short channel effects, and then Moore's law, right, how devices are being scaled down, right. And then transistors are used in different applications. I also talked about like the generic cases of high power switching, or maybe RF power amplifier, right, maybe memory devices, right. These may not be in the syllabus of many entrance exams, but these are something you should be generally aware of, like what are the things needed in a material or in a device to qualify it as a high power switching transistor or an RF amplifier, what are the figures of merit, what is how do the transistors work as memory devices, and so on. And finally, I had also talked about a little bit on the fabrication of many of these devices. In the clean room, things like lithography, right, etching to make the patterns and decide structures in the devices. Also we talked about deposition, like metal deposition, CVD, chemical vapor deposition, E-beam evaporation. Also we talked about things like doping like diffusion and ion implantation and so on, right. So this was in a way, in a nutshell, the course is all about. As I told you, we had touched on the very basics. Each of the things can be many, it can be studied in many details, semiconductor bands and energy band diagram with Kronig-Penney model, or other things. Many of these things have gotten multiple Nobel Prizes, they are very intense actually. Doping is very important. Even new semiconductors are being synthesized and discovered every day, and many layer 2D materials, they are coming up, and doping is very important in many of these new materials. Like if you get a new material, what will be a good dopant for it? So you have to depend on material scientists and chemists to tell you that. All these things we have studied in this course, and in many of these parts are very important for your GATE or NET exams. Many of these parts are important for understanding and to just get an interest for higher studies, for doing research or sort of thing. So for example, some of the questions that people give, which we have not solved many of the numericals here, but one of the questions that you should be able to think based on the concepts that you have learned. Suppose I tell you that, for example, and these are the questions that might be asked. Okay, suppose I tell you that I have a piece of silicon which is n doped, and from this is the left side, so this is x equal to 0 and this is x equal to L. It's some piece of semiconductor. I say that I am gradually increasing the doping from 10 to the power 15 to 10 to the power 16 per centimeter cube. Okay, I am increasing the doping gradually from the left side to the right side. I am gradually increasing the doping. Okay, gradually increasing the doping, and it is in equilibrium, which means when I say it is in equilibrium, it means there is no current is flowing and that the Fermi level is constant. There is no change in Fermi level. Okay, the Fermi level is constant. The change of Fermi level with respect to distance is constant. So how will you draw the band diagram? So one thing is that the Fermi level has to be constant, right? The Fermi level cannot have a slope. How will you draw the energy band diagram of this? So the Fermi level is constant. So assume this is Fermi level and this is constant. I know that at left side the doping is 10 to the power 15. So there will be some distance of the conduction band, and then this is valence band, for example. Okay. Now on the right side the doping is 10 to the power 16, which means the conduction and Fermi level will become closer. So conduction band will be here, valence band will be probably here, right. This spacing, this conduction band and Fermi level spacing will become lower because the doping has increased. If the doping is lower, then this spacing of conduction and Fermi level will be more. You remember that? But this is because equilibrium, Fermi level cannot change. So the conduction band has to bend essentially. Okay, conduction band has to bend like this. Okay, and the valence band also has to bend. The band gap, of course, is the same everywhere. So this is how a band diagram will look like. Okay, there will be an inbuilt field inside it. Of course, the way in which the bands will bend depend on how are you changing the doping. Are you changing the doping linearly? Are you changing the doping exponentially, logarithmically, and so on? In this case, you see conduction band EC is changing linearly, which means your doping is changing exponentially. You have to prove that yourself. I will not tell you that. Okay. So this is one way. So this is one, something that you have to think on your own. For example, suppose you are given a very highly doped P plus semiconductor and a junction with N minus lightly doped. For example, P side is very highly doped, extremely highly doped, and the doping level is not given. When you say extremely highly doped, it means on your P side, suppose this is your P side, your Fermi level is almost at the valence band. Okay, it's very highly doped, that's why it's almost there. And N minus is a lightly doped, so all your depletion will fall only on the N minus side. The depletion will not be on the P side, which means if this is your Fermi level, it has to be equilibrium everywhere, no? And then your N minus is very lightly doped, so it will be like this, conduction band, this is valence band. So all the depletion will drop across this only. Okay, all the depletion will drop across the N type N minus only. It will not drop across the P side because it's very highly doped. Now the N type doping on the N side, suppose it is given to be 10 to the power 15 per centimeter cube silicon. How will you find out the built-in potential? So the built-in potential is this value. So that value is built-in potential. How will you find out? That value is nothing but that is equal to this quantity, if you see very carefully, minus this EC minus EF. So EC minus EF, this quantity, if I call that phi n, that quantity is nothing but KT by Q ln of NC by ND. Do you agree? NC is the conduction band density of states, ND is the doping that is given. So that value you can find out because this is given, and NC for silicon will be given, that will be around 3.10 into 10 to the power 19. So some value will come out here, maybe 0.2, 0.3, whatever, right? So that value is phi n. So your built-in potential, this quantity is actually this amount minus the phi n. Now what is this amount? If you look carefully, that amount which is this is actually this, which is the band gap of silicon, right. So your built-in potential, band gap silicon, right. So built-in potential is equal to actually the band gap of silicon minus phi n. So band gap of silicon is 1.1 minus whatever this value you get, this value, no, that is K 0.026 ln of 3.2 into 10 to the power 19, that is your NC divided by 10 to the power 15. Whatever value you get, that you subtract here, and you will get the built-in potential. Of course, here I am assuming that because of high doping on the p side, the band gap of silicon has not shrunk, because at very high doping the band gap will become slightly lower, that I have not considered, okay, but that is okay. Okay. So this is how you will find out the built-in potential of this very highly doped P plus N junction, for example. A few years back there was a question on gate, I think there was an N plus N minus junction. These are called isotype junction, homo junction, isotype junction, because they are of the same type. So you have, for example, a very highly doped N plus, so the Fermi level is very close here, and then you have, suppose, another same silicon, same material, so silicon, so same band gap, for example, but you have same band gap, but your Fermi level is little below, because it is lightly doped. If you join them, what will happen? If you join them, essentially what will happen is that your band depletion will primarily fall across the lower dope side, no. So what will happen is that if you join them, then your, this is a Fermi level, right. So this is your conduction band, this is your valence band. So there will be slight left, and then like that, right. Most of the depletion will be on the N side, okay. We cannot call it exactly depletion, because there is carriers here, it is not depleted per se, it's N type dope only, but the built-in potential is the built-in potential corresponds to this quantity, which is nothing but this quantity, okay, minus this quantity. This quantity, if I call it phi n, and this small quantity if I call it, say, psi n, that in, you see my point, right, this minus this is the built-in potential. So phi n is nothing but kT by q ln of, sorry, NC divided by ND, I call it, this is ND2 and this is ND1, both are N type dope, no. One is suppose 10 to the power 18, one is suppose 10 to the power 16 per centimeter cube, okay. So ND2. Similarly, psi n will be equal to kT by q ln of NC by ND1. So the built-in potential is equal to phi of n minus, sorry, psi of n, okay, minus psi of n. You see my point, right? This minus this quantity will give you the built-in potential. So that will be equal to kT by q, right, ln of ND1 by ND2. So the doping, the ratio of the doping on both sides basically will give you that, okay. So that will be 0.026 ln of 10 to the power 18 by 10 to the power 16 or whatever, okay. That will give you the built-in potential, for example. So these are some mock examples I have told you for, for example, your PN junction. Similar questions can be asked in each of the other topics. For example, you have learned Maxwell-Boltzmann equation. When you have conduction band, we have valence band, and then there is this Fermi level. I told you that Maxwell-Boltzmann holds true when this gap EC minus EF has to be greater than or equal to 3 times kT, right. So if I have a band gap of a semiconductor is very small, suppose the band gap is 0.05 eV, suppose the band gap of a material is very small, 0.05 eV, and the room temperature energy kT is 0.026 eV. Now if you have a semiconductor whose band gap is 0.05 eV, then doesn't matter where you have the Fermi level, this will always be less than 3 kT, because the band gap is itself less than 3 kT. Now will Boltzmann-Maxwell distribution equation hold true? No, it will not hold true. At what temperature will it hold true? At that temperature only when such that 3 kT will become low enough such that the Fermi level can be in the middle of the gap, so that Eg by 2 has to be greater than or equal to 3 kT, because Fermi level can be at max mid gap away from the conduction or valence band. So the band gap by 6 K less than or equal to temperature. So from this value you can find out the temperature, maybe 50 Kelvin or 40 Kelvin, whatever you will get. Below the temperature only you will be able to apply the Maxwell-Boltzmann rule. So there are many conceptual questions that might come up, right? Similar questions might come up in BJT or MOSFET, and all the routine questions that come in many entrance exams are not very difficult. You know, they might give you some very similar questions, like for example in gallium arsenide, one of the questions in entrance exam was like gallium arsenide, if I dope it silicon, so what will happen? If silicon occupies group 3 sites, which is gallium, then it will be n type. Okay. If silicon occupies the arsenic sites, which is group 5 site, then it will be p type. So those things you should remember. For example, those are simple questions that are given, right? Sometimes they might give you questions ki, you know, I have a PN junction, a normal PN junction, I have a normal PN junction, and at 0 bias the depletion width suppose is, you know, 1 micron. Suppose at 0 bias depletion is 1 micron. So when I said 0 bias, then you know I'll say that W equal to, if you recall, 2 epsilon by Q VBI built-in potential 1 by Na plus 1 by Nd equal to this, right? Now this is 1 micron. Okay. So the question is, at what voltage will this depletion become smaller and become like say 0.5 micron? At some forward bias voltage it will become smaller, no? So it will become 0.5 micron at some forward bias voltage. So 2 epsilon by Q VBI minus the forward bias voltage 1 by Na plus 1 by Nd, right? So if you divide what voltage, you want to find out the question what voltage you have to apply. So you divide one by the other, so it will be 1 by 0.5 whole square will be equal to, everything will go cancel out, VBI by VBI minus VA. Now the built-in potential might be given to you in the question, or if the doping is given you will find out the built-in potential. So this will be equal to 1 by, this is 2, so 2 square is 4, so 4 equal to VBI minus VA. So if VBI is known, say this is given to be 0.7 volt, then 4 equal to 0.7 minus VA. So this will come out, you can find out VA, right? You can solve and find out VA. So that kind of forward voltage is needed. So these are simple questions based on equations and formula, but there can be more conceptual questions, you know, as I told you, something that are not, you know, generally taught, or for example something that is like the grading, like if you gradually dope the semiconductor, what will happen, for example, right? So those kind of questions are not covered in many of the textbooks. In many of the thinking problems also, you know, you have to think hard about the situation, what will happen if that is the case. For example, you know, if I have an N minus semiconductor and N minus semiconductor, in between is undoped, then how will it look like? It's slightly doped on both sides. So the Fermi level, if you draw the Fermi level EF, then you know it will be like N minus, and then there's undoped, and then again it will N minus, right? Like that, it will be like that. Okay. Suppose I have a sheet. Suppose I have a sheet of very highly doped P plus here. How will it look like? Then that will pull the band up. So it will be like that. Okay. It will pull the band up, because the P type will try to make it the Fermi level come closer to conduction valence band, right? So those kind of things are conceptual dependent, and you should be able to do that. Okay. So these in an essence are sort of the things that one should be prepared of. And again in the transistors, in sort of BJT and MOSFET and so on, there are many equations that I had given you. You can use those equations and solve most of the simple straightforward numericals, but you know many of the questions might need to think. For example, you have to think harder in terms of, for example, if I have a BJT, I told you that I have a emitter, I have a base and then collector, and then base emitter has a junction here. You know the operations of the BJT in a conventional forward active mode, but there are other modes also, like reverse mode, there is a saturation mode, there is a cutoff mode. Any standard textbook will tell you what it is. We have only discussed about mostly forward active mode, which means the emitter base, this junction is forward biased and this junction is reverse biased. Both of them can be forward biased, both of them can be reverse biased. They have different modes. But suppose I shine light on the base collector junction, what will happen? There will be photocarriers generated in the base junction, electrons will go to one side, holes will go to another side. What will happen now? What will happen to the base current? What will happen to the collector current? So that kind of things you have to think, and also you know ask questions about it, right? So there are many questions that you can think about, and always ask questions. So the idea is to keep asking questions and trying to see from the basics of semiconductor point of view, the device point of view, how it will work basically. Okay, that is in a nutshell the question is. So that is all about. So let us end the last class here. We have given you a summary of whatever we have learned and the topics that we have discussed in this course. We have also discussed about many of the devices, and you will see that in the course as we go ahead there will be assignments, there will be also end term exams. Many of the questions will be slightly different from the questions that you find in many of the entrance exams. Whatever we have learned in this course, although not at very advanced level, but hopefully it will be enough to create an interest in you, and it will be enough to make you think in the exam, in the assignments. Okay. So, so this was the end of the lecture, and also the end of the course. We'll look forward to interacting with you over the live sessions and assignments and exams and so on. Please feel free to email me or email my TAs. There will be 3 teaching assistants in this course, and they will be also very actively involved in answering your questions and clearing your doubts. We are always reachable on email, so please feel free to do that. And so with that, I will end this course, as well as also end this the last lecture. Although the lectures have ended, as I told you, I will always be in touch over email and live discussions. Okay. So thank you for your time, and with that I will conclude the course. Okay. Thank you.